Alright, so in this module we are going to look at some applications of computational electromagnetics to modeling antennas. What is their impedance, how do they radiate. So to start with, we will actually take a slight bit of a detour. So far what we have been seeing in from Maxwell's equations is that if you give me current, I can calculate E and H. That is a straightforward route, right. So you give me J and maybe even M if you have magnetic current, and out comes E and H. This is a standard route, but there is another route where you go from these currents, you calculate something else in between. These are magnetic and electric vector potentials, okay, and from here you go to E and H. So these are two routes, this is route 1 and this is route 2. The source and destination of these routes, I mean, is the same, but the intermediate steps are different, and for antenna problems it is generally true that this second route is easier. Okay. In our scattering problem so far we have not encountered this A vector, right. You can also formulate the scattering problem in terms of the A vector. Okay. It's all basically those 4 Maxwell's equations, how you treat them. So since we have not yet looked at these vector potentials, we'll introduce them. And then we will deal with the simplest antenna, which is your Hertz dipole, and then go to more complicated cases, right. So let us look at these. So scalar and vector potentials. So let us just write down our Maxwell's equations. So the first one we can write as curl of E is, right. So minus j omega mu h. Okay. So we are going to assume e to the j omega t, monochromatic case. Okay. Next equation is curl of H is j plus j omega epsilon E, right. Third equation is del dot B is equal to 0 and then del dot D is equal to rho. Now, what we will deal with is, we are dealing with non-magnetic materials, okay, and moreover, so when we are talking about antenna problems here, the antenna is sitting over here, that is radiating out in free space, okay, and this is usually free space that we are talking about. So of course mu is that of free space, and in general we are not talking about magnetic material over here. So this condition over here I can rewrite as simply del dot H is equal to 0. So what, so sort of the starting point for these vector and scalar potentials is this equation over here. Okay. Looking at this, you can easily, I mean, by using your standard identities in vector calculus, this is satisfied by any vector of the form of what form? Can I replace H by something and make a statement that will always be true? Curl, right. So the idea is that divergence of curl is always 0 regardless of what the field is. So I can write del dot H is equal to, so sorry, that implies that H is equal to curl of A, okay, and I don't I mean A could be anything, right. This relation will always be satisfied. So what I am doing is, from Maxwell's equations I am finding out something which is consistent, right. This is not inconsistent with Maxwell's equations. So this was the first idea, right. The second idea that we are yet to use, but we will use, is that we had done this right in the beginning of the module studying vector calculus, that any vector field is completely specified up to a constant if you give its curl and divergence. Okay. So, it is completely specified by its curl and divergence. Okay. So, for this vector field A, what have I specified? Right. So far I have specified the curl. So, I have taken a vector field A and I have said curl of A should be equal to H. So, one degree of freedom is still there with me, the divergence, which we will sort of exploit later on. Okay, so now that I have this, what can I do with it? So let's number our equation. This was 1, 2, 3, 4. Okay. If you had a magnetic medium, what would you have done instead? Then I would have taken del dot B equal to 0. I could have said B is equal to curl of something, and that's commonly done. So you will find some places A is defined in this fashion. Actually, let's do that. Let's define our. Why make this special case? Let's keep this as B is equal to 0 itself, and all we have to do is this. Okay. So then I don't have to make any special case that mu is magnetic, not magnetic, whatever, right. So this is right, because B is equal to mu h. Okay, so this becomes my equation 5. So now I can combine 1 and 5, because from 5 I get a relation for h, correct. So what happens now? So curl of E becomes equal to, what can I write? Minus j omega curl of A, which I can combine these curl options, variables over here. So this becomes E plus j omega A is equal to 0. Okay. Now can I simplify this further? So this relation over here is always going to be true if it is like the gradient of something, right. So if this is of the form, so this is equation 6, right. If E plus j omega A is of the form, let us say minus grad phi, then 6 is always true. Okay. The minus sign is just convention, does not matter. So we are just using our standard vector calculus identities. So what does that give me? It gives me E is equal to minus j omega A. Notice that mu nicely cancelled off, minus grad phi. Okay. Let's call it equation 7. So what did we start with? We started with A. From A I have, supposing I give you A, I have equation 5, which gives me H, and once I get H, I can, for example, take curl of H and get E, right. And I also have a relation for E in terms of A and phi, right. So A is called the magnetic vector potential, and phi is called the scalar potential. Right. So far we have not said anything about this point number 2. Okay, so we'll come to it. So what could we do next? Take curl of first equation, and then that will allow us to substitute, right. So let's write it down over here. So my first equation was curl of E was equal to minus j omega mu h. Now if I take curl on both sides, I get del cross E, and I will get a minus j omega A, because curl of H is that 1 by mu A is there. Okay. Then next, what do we do next? Well, that okay, so let's do that. So I will get del dot E minus del squared E is equal to minus j omega A. Oh wait, I think I messed that up. This is curl of mu h when I just take curl on both sides, right? And which is equal to minus j omega. Curl of h I said is yeah, so right. Curl of A is h. So now I substitute this curl of this h over here. So I will get the mu will cancel off, right? So I will get a del cross A. Yeah, that's the better way. And can I simplify this left hand side instead of writing it in this fashion? Yeah. So this is okay. And what about the left hand side? Should I leave it as del cross E or should I do something else to it? I should apply the identity. Okay. Can I not do something else? So right. So curl of h, remember we have j plus j omega epsilon E. Okay. So then what? So this is taking us to one route where possibly we will have to apply the vector calculus identity to E itself. This was equation, the root for equation 1. If I take equation 2 itself and don't apply any curls, what happens here? So let's take this. Here I substitute h as, I can substitute h over here in terms of this relation, right. So this will become 1 by mu del cross A, right, and that will be equal to j plus j omega epsilon. Now E I can substitute over here as, where did it go? Equation 7. So what is equation 7 saying? E is in terms of A and phi, right. So this becomes minus j omega A minus grad phi, which is actually what I want, because I wanted to get rid of the fields and have some relation purely in terms of these new quantities that I have got. So the first equation was giving me a bit of a trouble, because then I have del cross E. What do I do with that, right? So that route will also bring us to the same point. This is a shorter route. Now let's just simplify this further. So here I can apply the vector calculus identity. Okay, let's take the mu on the other side. So this will become del first term. Okay, this will become mu j. Then I have, what else do I have? I can take this minus sign outside. So plus omega squared mu epsilon A. What else? Minus j omega epsilon mu grad phi. Okay. So let's combine all our terms together, right? So let's write this as del squared A plus omega squared mu epsilon A. Let's keep that on one side. Okay, and let's gather the remaining divergence terms. So I have minus. Have we got all the minus signs correct over here? Yes. Okay. So minus. Let's see. Now I have I want to write this as del, and let's gather all the terms inside over here. So the first term will be del dot A. Okay. Okay. Then I'll have a plus j omega epsilon mu phi is equal to mu j, right. Is this true only if epsilon and mu are not functions of space? Let's look at epsilon, for example. So I took equation 2, epsilon is a function of space, right. I did not take any curl, I simply substituted for h over here. So del cross A happened over here. So actually I have not made the assumption that epsilon is a function or not a function of space. Yes, yes. Over here, if when I did this over here, I assumed that you're right. So over here, implicitly, when I took this the del operator, I have made the assumption that epsilon is not a function of space. Okay, and why is this sort of okay? Because I am trying to solve Maxwell's equations for an antenna usually radiating in free space. So, free space I can make that assumption. I also made the assumption that mu is not a function of space, because when I substituted for h over here, there was a 1 by mu over here which I took outside the curl, right. So, it came from here and went here, okay. That will be minus mu j. Will it be minus mu j? I think he is right. This should be minus mu j. Yeah. Okay. So does this equation, let's call it equation 3, right? So does this equation 3 look like does it look like something that we have seen before? It looks a little bit like Helmholtz equation. It's not Helmholtz equation. Why? That this big term over here, right? So it's somewhat, so more generally we will, instead of calling it Helmholtz equation, we'll just call it a vector wave equation, right? So it's like a vector wave equation. Do I know how to solve this? We do. This is a horrendous equation. I don't know how to solve it, right? But here is where I use fact number 2. Fact number 2 is divergence and curl both have to be specified. So, if I now specify the divergence of A and what is the most natural choice for divergence of A? Negative of this term. Okay. So, supposing I specify this degree of freedom was there in my hand, right. So, then what happens to equation 3? I get del squared A, okay, plus omega squared mu epsilon A is equal to minus mu j, equation 4, right. I get an equation which I can solve. This is a vector wave equation, I know how to solve this. So, this choice, remember this was a choice, I need not have made this choice and I could have chosen to solve an even more difficult problem. It is not unsolvable, numerically I can solve it, but this choice is what is called the Lorentz gauge. So, remember this is a choice of the divergence. There is another gauge called Coulomb gauge where some other choice is made for divergence of A. Okay. So, it depends on the problem. You want to, basic philosophy in most EM problems is make those choices which makes life easy. So, here making this choice makes life easy because you know I get this nice vector wave equation. And do we know how to solve this? Yes. What is the straightforward way of solving this kind of an equation? Green's function. In more generally, integral equation methods, right. Particularly so because this guy is constant, it is not a function of space. So, I know how to solve this equation, it will give me the solution will be what? So, supposing I want to solve this, yeah, yeah, exactly, yeah. So, if we solve for A, well, we will come to that, we'll come, once let us settle how to calculate A, okay. No, Coulomb's gauge does not make this choice for divergence of A, it makes some other choice. So, remember, so finally what should it be consistent with? I should get the same E and H regardless of whatever choices I have made, and you will get the same E and H. Your form for A and phi will be different, but that does not matter, okay. So, actually let me mention there is a slight bit of I should say, I do not know if I should use the word controversy, but ambiguity in what I said. As far as electrical engineers are concerned, this A and phi are purely mathematical constructs which are helping us solve the problem. That is how electrical engineers look at it. Physicists, however, attribute some physical importance or significance to this A and phi. Electrical engineer says all we can measure are fields. Physicists say that no, there is some significance to A, and there is something called the Aharonov-Bohm effect, which tries to measure or give a physical significance to A, and they say that in some highly specific quantum regime there is some physical meaning for A. So, A also should be unique, right, and so this gauge condition and all has to be seen a little bit more carefully. In usual antenna problems and all, we never run into that issue. So, I mean we will not go further, but I will write the name over here, you can look it up. Aharonov. Okay, so but that is an interesting detour in another direction. So, any other questions? Okay, so we know how to solve this equation, and the solution is by Green's function. Can you tell me in words what is the solution? Yeah, in NED. It is the convolution, it is the convolution of impulse response with the forcing function, right. So, what is the, so if I have defined my del squared G plus K squared G is equal to minus del, right, delta function. So, if I have a minus sign here in the definition, then my A is given by the convolution of mu j. So, R, let us write it properly. So, this is R is equal to R prime G of R prime d R prime, a vector, okay, in general 3D. I mean you can, if the problem is 1D, 2D, 3D, that those many integrals is what you will have, right. So, this is pi integral. Yeah, so if you assume 3D Green's function, but the problem is 2D. Yeah, you have to do it a little carefully, because if one direction there is no physics happening in one direction, in some sense there is an infinity in that direction when you try to integrate in that direction. So, something is happening in xy, but nothing changes in the z direction. So, if I integrate along the z direction for a function that does not change, what will I get? I will get infinity. So, if you can deal with that and cancel it off correctly, then you will be fine, but it is a little bit more work to do it that way. So, let us just sort of summarize what all we have. So, sort of the flow of problem, right. So, what is given to you is, in any problem is given, let us say the current J. If I give you the current that is flowing in some antenna, what can you do? I can find out A as the convolution of mu j and G from this equation over here, equation 5, right. So, that means I get A. The second thing, once I get A, obtain what? H from it. Why? Because what is the definition of, right. So, I can use this relation over here, H is 1 by mu curl of A, okay. Third is, what is the third thing that you are interested in? Electric field, okay. In general that is our objective, find the electric and magnetic fields. So, E is going to be, what choices do I have? So, yeah, so in terms of this definition over here, where did it go? Yeah, here. So, E is minus j omega A minus grad phi, and we have found out a relation for phi over here, right. So, from here I can write down that phi is equal to j by omega epsilon mu epsilon del dot A, right. So, this will become minus j omega A minus divergence of j del dot A divided by omega mu epsilon. everything is in terms of A. So, this is one way of doing it. Is there a simpler way of doing it for finding E? F. I don't need any F. Yeah, I know. There is an electric vector potential, but you are recalling from memory. Recalls from logic. Maxwell's equations, right? So, what is, if I know H, can you give me E? Yes. What is E? So, I can use curl of H because I have already calculated H in step A and step 2 is J plus J omega epsilon E. I know H, I know J, I get E, right. So, all I have to do is take curl of H. Uniqueness theorem. No, okay. So, first of all, statement of uniqueness theorem was not that if I know epsilon mu, the fields are unique. Statement of uniqueness theorem was if I know the tangential E and H fields or some combination thereof over a closed contour, then I know the fields everywhere and they are unique. So, it is not enough for me to just know epsilon mu. I mean, there are infinite possible fields given free space, for example, right. Every time I change a current pattern, I get a different radiation field. So, the gauge condition is not violating the uniqueness theorem, because whatever different gauge condition I choose, I get the same E and H. If I get the same E and H, the tangential fields on this contour are the same. So, uniqueness theorem does not get violated. You get the same fields. It is like an intermediate variable. It is just a detour. So, you get the same, you put the same, right. So, let me write this down. Same we go ahead. So, in any antenna problem, this is going to be what we will do, okay.